The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
Okay, I just wanted to just briefly remind you of some of the periodic trends that we talked about. As you go across the periodic table, both the electron affinity and the ionization energy increase. They increase because the nuclear charge increases. Remember, the potential energy of interaction is Z times E, where that's the nuclear charge, times E over 4 pi epsilon naught R. Z increases as you go across the periodic table here. As you go across, R is remaining the same because you're essentially still in the same shell. And so what increases is that attractive interaction, meaning the electrons are more strongly bound, meaning ionization energy and electron affinity increase as you go across. And also, this also means that as you go across, R, the radius, decreases. All right, the radius decreases again because Z increases. The nucleus is pulling the electrons in closer. Since they're all in the same shell, R is remaining the same. And so the overall effect is that the radius of the atoms decreases. As you go down the periodic table, the ionization energy and the electron affinity, they decrease. They decrease because it's the R dependence here that takes over. Z is, of course, increasing, but not as fast as R. As you go down the periodic table, you're going to shells that, on the average, are further out from the nucleus, and that dependence takes over, causing EA and IE to decrease. And then the radius, well, the radius, of course, then increases. Okay, because as you go down, you're putting the electrons into shells which are, on the average, farther away from the nucleus. All right? So that's just a review of those trends. And then finally, I want to just define another term, and that is the electronegativity. Sometimes we give that the symbol chi. The electronegativity is an empirical quantity. We're going to use Mulliken's definition for the electronegativity. There's a Pauling definition. Mulliken's a little bit more straightforward. And that electronegativity is defined as 1/2 times the quantity ionization energy plus the electron affinity. All right, so the electronegativity is proportional to the average of the ionization energy and the electron affinity. The electronegativity is a measure of the tendency of an atom to accept or to donate an electron. All right? So if you look at the periodic table here, you have atoms in the upper right-hand corner of the periodic table. Well, they have high electronegativities. They are good electron acceptors. They have high electronegativities because they have high electron affinities. Adding an electron to them means that there's a larger amount of energy release. Right? The anion is much more stable than the neutral. And the electron affinity is minus that energy change, you remember from last time. So these atoms here, with their high electron affinities, are good electron acceptors. They're also good electron acceptors because their ionization energies are also high, which means you have to put in a lot of energy to pull an electron off, so they don't like to donate electrons. Rather, they are good electron acceptors. And then the elements that are in the bottom left-hand corner of the periodic table have low electronegativities. They are good electron donors. They're good electron donors because their ionization energy is low in this part of the periodic table. You don't have to put so much energy to pull an electron off. They're also good electron donors because their electron affinity is low. You don't get as much energy back when you put an electron on them. So these are good electron donors. High chi here, these are good electron acceptors. And one thing you already know probably is that some of the strongest ionic bonds are made between elements in these two corners of the periodic table. Right? An ionic bond, as we're going to talk about, is one in which the electrons are not shared equally. And so these strong ionic bonds occur between elements with high electronegativity and low electronegativity. Okay? So that's that concept. And then finally, one other kind of odd and end here. That is this term isoelectronic. All right? I've listed here a bunch of atoms and ions that are isoelectronic. Isoelectronic means having the same electron structure. All of these atoms and ions have the electron configuration 1s2, 2s2, 2p6. So for example, this nitrogen, nitrogen -3, it has added 3 electrons to be nitrogen -3. It has added 3 electrons to get this electron configuration, this rare gas configuration, this octet configuration, which is a very stable configuration. Aluminum, it has 3 electrons removed to obtain this particular electron configuration. All right? The common ions, ions that you see commonly in nature, are ions that in fact do have this octet configuration, this electron configuration of an inert gas. So for example, you will often see compounds with nitrogen -3. You won't very often see a compound with nitrogen -2 or nitrogen -1 because those aren't as stable as nitrogen -3 given this rare gas or the octet configuration. Okay? All right, so that's just a little odd and end. I just wanted to make sure that everybody was on the same level with the understanding of the word isoelectronic there. Okay? Okay. Well, now what I thought I would do is talk a little bit about wave functions and the usefulness of wave functions. And this is going to be on the sideboards here. I wanted to just show you in kind of in simple terms how a wave function actually determines the intensity of some transition. Many of you have asked me about the intensities of transitions. And so I thought I'd show you just a little bit about how these wave functions determine the intensities of transitions. All right, so first of all, I have to explain this diagram to you. This is going to be a diagram for a hydrogen atom. That's what we're going to talk about here. And what we are going to start with is an energy level diagram for the hydrogen atoms. That's what this axis is. And so I'm plotting in that diagram energy going up. And I plot the energy level for n equal 1. I plot the energy level for n equal 2, n equal 3, all the way up to, I think I plot n equal 235, right, which is really very close to 0. All right, so that's part of what's on this plot right here. Okay? Whoops, can't get to my... Okay, that's what's on this plot, n equal 1, n equal 2, n equal 3. But then, what is also typically done on the same plot is that the potential energy of interaction is plotted as a function of r. So on this axis here, kind of superimposed, is this distance r. Okay? And we plot often the potential energy of interaction. So the potential energy of interaction kind of looks like that, right? This potential energy of interaction is the Coulomb interaction, minus e squared 4 pi epsilon naught times r. So that's what that line is on your on this plot. All right. So then what we do is we actually plot the form of the wave function kind of on top of the energy levels. All right. So what we do is to say, for example, take the n equal 1 wave function, which starts at r equals 0 at some finite value and is just an exponential decay. And we plot it on this diagram, but we use the n equal 1 energy here as the value of psi equals 0. Okay? So in other words, the n equal 1 wave function looks kind of like that, right? So this level here is psi equals 0. This is the value of psi, whatever it is, at r equals 0, and there's just an exponential decay. So we plot the wave function on top of that energy level. So in other words, this is a complex diagram here. And you're going to see, if you take any courses beyond this, you're going to see this diagram a lot with energy levels and wave functions plotted on top of them. All right, and then the n equal 2 wave function is plotted on top of the n equal 2 energy level. So again, at r equals 0, it's some finite value, right? And then it drops. At some value of r, we got a node for n equal 2 here, right? So the n equal 2 is the psi equals 0. So right here you got a radial node, and then it goes up, and then it comes back, goes down to a negative value, and then comes back up. So that's n equal 2, and so forth and so on, right? N equal 3 looks like this, right? It has 2 radial nodes. That's what that diagram is showing you here, all right? And then we get to n equal 235. Here's the wave function, all right? If this is a hydrogen atom and you got n equal 235, how many radial nodes do you got? 234. So this wave function is passing through this origin 234 times, all right? That's the wave function. Then it tails off. There's always an exponential dependence there. That's what that wave function looks like. Okay, now, how do these relate to the intensity of some transition? Well, the intensity of a transition is related to the overlap between the wave function of the initial state and the wave function of the final state. What do I mean by overlap? Well, by overlap, I mean you take the wave function here of the initial state, and so I'm going to pretend we got a hydrogen atom in the 235th state. This is its wave function. And that hydrogen atom is going to be relaxing to the n equal 1 state. All right? So what I'm going to do to get the overlap is I'm going to take the product of the wave function of the initial state times that of the final state. And essentially, I'm going to integrate that resulting function. So I'm going to multiply these 2 wave functions together. And I'm going to integrate over all r the resulting function. That's what I mean by overlap. But there's another term here. There's an r here, too. That r is important. It has to do with the transition moment dipole. And we won't go into that, but it is there. Okay? But it won't affect the argument I'm going to make for you right now. All right, so we take the wave function of the initial state, multiply it by the final state times r. And then we integrate this whole thing from r equals 0 to infinity. It's that, and then square it. And that quantity is proportional to the intensity of some transition. All right? Okay, so let's do that. Here's psi, n equal 235. We're multiplying it by psi of n equal 1, and actually multiplying it by r. And what we're going to see, if we just look at this product here, or if we just looked at psi n equal 235 and psi n equal 1, if we just looked at that product, we're going to multiply this times that. In a graphical form, it's going to look like this, right? It's going to go up, down, up, down, up, down. It's going to oscillate and then tail off in an exponential way because we're multiplying this up, down, up, down, up, down times this exponential decay. It's going to look something like that, right? Okay. But now, we're going to integrate this resultant curve. But what you can see is that the area above this curve is equal to the area below this curve approximately. And when we integrate something, we're calculating the area underneath the curve. So these positive areas are going to cancel these negative areas, right? And the result is that this integral is going to be very small. And the result is that the intensity of that line is very low. All right? So the intensities are proportional to this overlap, the overlap of the initial state wave function and the final state wave function. And you can see here graphically, right? You can see graphically how if you integrate that product, in this case, the positive areas cancel the negative areas, and hey, you don't have a very intense transition. All right? However, suppose we look at the transition from n equal 3 to n equal 2. Well, here's the n equal 3 wave function. Here's the n equal 2 wave function. And our intensity expression says that, hey, we got to multiply these two. So let's do that. Let's multiply n equal 3 times n equal 2 here. Well, the result, if you excuse my not so great drawing, the result is we start out with a very positive function here, but then we've got two negatives here, which make it a little bit less negative and positive. But then we have a positive here times a negative, and so what that makes is a large area here, or a large area that's negative. And if we go and integrate that, well, now we don't have the same cancellation of positive and negative areas. So when we integrate that, that transition intensity is large. All right? Or that area is large, therefore the intensity of that transition is large. Bottom line, that is one of the elements that dictates the intensity of a transition. It is also one of the elements that dictates the intensity of your photoelectron spectra. Somebody asked me about it the other day. I had drawn lines in the photoelectronic spectra that were of the same intensity, 1s, 2s, 2p6. Somebody said, well, you have more electrons in the 2p state. You know, why don't you have a larger number of electrons coming off? And the answer is that's part of what goes into determining the intensity of the transition, but there's more to it. It's not just the number of electrons. And here's one of the elements that goes into determining the transition of the intensity of some transition. It's the wave functions and the overlap between the final and the initial state. Okay. And then I just wanted to also show you here for this atom in the n equal 235th state, I plotted just for fun, kind of schematically, what the radial probability distribution would look like. All right? So that's just r squared times the radial part squared. And of course, since the wave function goes like this, oscillates, that's what the radial probability distribution is going to do. And you're going to see 234 nodes here, 234 values of R, that is going to make the wave function be equal to 0. And then way out here, you're going to have a feature. That last feature here is going to have the maximum probability, and that's your value of R. That is most probable. And it turns out for n equal 235 that the most probable value of R is 43,800 angstroms. So that's, about 4.38 times 10 to the minus 6 meters. So this is a really large hydrogen atom, n equal 235. So do they exist? And the answer is yes. They do exist. They exist particularly in outer space, where there's lots of UV radiation to get these hydrogen atoms up into these very excited states. And they exist in deep outer space where the temperatures are pretty cold, right? And you need those cold temperatures because, this hydrogen atom isn't very stable in n equal 235. And if you went and you calculated here as, I think that I did somewhere here, okay. If you go and you calculate, so now I'm going to draw a line here. This is going to be n equal 235. Right? And this is the 0 of energy. This energy difference here is about 4 times 10 to the minus 23 joules. Okay? Whereas at room temperature, just talk about the thermal energy. Thermal energy at room temperature is about 4 times 10 to the minus 21 joules. Okay? You can see that any little fluctuation at room temperature, since this is 2 orders of magnitude larger than what this is bound by, any little fluctuation would kick this very weakly bound electron up and ionize it, and it would, right? So you can really only see these in environments that are very cold, where you don't perturb these, what they're called Rydberg atoms sometimes. I think in the laboratory, the largest Rydberg atom that has been made has been n equal 180 or n equal 200 or so. Okay? Okay, but anyway, that was really just for fun. I wanted to tell you about that. Okay. And now there's another little a tidbit that I want to talk to you about. And that has to do with how knowing something about the energy levels in an atom leads to a nice practical device like a helium neon laser. All right? Okay, so we got to take a look at the neon energy levels. And so we got another discharge lamp here, and we have some more of these glasses here so that you can resolve the neon lines here, and the TAs will get them out. So here's our neon discharge lamp. Okay. So you can resolve here the neon spectrum. The spectrum that you should see should be what's shown on the side walls here. Let me turn off the light so that you can see it a little bit better, hopefully. You can see lots of lines in the case of neon, because we have lots of different occupied states. The glasses that I have actually are doing a phenomenal job in resolving those very closely spaced lines. I must have a better quality glass today. Okay, and if you look at the side walls, you can see that I drew one of those lines. One of those emission lines is at 632 nanometers, which is the emission line of a helium neon laser, but it's really a neon transition that we'll talk about in a moment. I drew it as very thick on the board because when I looked at the discharge lamp and I drew that picture, my glasses didn't resolve those lines so very well, and so that one looked really thick to me. But at least my glasses, I can really see lots and lots of discrete lines. All right? But it is this transition, 632 nanometers, that is the output of the helium neon laser, which is the red laser that I use sometimes in the lecture here to point. It is the basis of the laser that's used in the grocery stores to scan the prices on your items. And turns out that what's going on here is the following. If you look on the side walls, we've got neon in the ground state before we turn the discharge on. And then when we turn the discharge on, that pumps energy into the neon atoms, such that one of those electrons, sorry, one of those electrons, the 2p electron, gets promoted into the 5s state. All right? And then, of course, that atom wants to relax, and so here comes again, that 5s state relaxes, that electron relaxes to the 3p state, and it is actually that transition that occurs at 632.8 nanometers, the basis of the helium neon laser. It's that transition from the 5s to the 3p, so it's not all the way down. And ultimately, of course, that state relaxes. Okay, but what's going on in the helium neon laser? Well, in the helium neon laser, we have a discharge ignited where we have a lot of neon atoms here in this excited state with the one electron in the 5s state, right, as I show you. And that is emitting. Photon comes out. But what's happening here is that that photon that is emitted, that photon is able to, because of the construction of this laser, that photon is actually able to contact or to interact with another neon atom in this same excited state, that 2p5, 5s state. That photon interacts with this excited atom. When it interacts with that excited atom, what happens is that that photon stimulates that excited atom to actually emit a photon of the same energy. All right? So this photon stimulates this excited atom to release its energy right at that time. So the result is that you've got two photons coming out. They're going to come out in the same direction, and they're going to be what's called coherent. That is, their phases are going to match. If you think now the photon as a wave, they're going to be coherent. And the result is that you're going to have some radiation that is going to be twice as intense because they're coherent, they're in phase. All right? And then what happens is that these two photons, they each then interact with another neon atom in this same excited state. And each of those photons stimulate another atom to emit photons. And the result is now that you have 4 photons being emitted, same frequency, same direction, and same phase. All right? And it's in this way that we amplify the light in any kind of a laser. This is what's going on, this process of stimulated emission, where you have a photon that now is exactly the frequency of the energy difference of the transition you're going to make in this excited atom, right? It stimulates that atom to emit that photon. The 2 photons then come off coherently. And then these two interact with two other atoms. Now you got 4 photons that are coming off. That's the process of amplification in this, in any type of laser. Okay. All right. Now, of course, in order to make this work, you've got to have a lot of these excited neon atoms around, right? Because you have to be able to have a photon interact with them before they just emit spontaneously. This is stimulated emission. The other kind of emission that we were talking about is spontaneous emission. So in other words, you've got to have a high concentration of these excited neon atoms so that the photons that are originally emitted here by just spontaneous emission can interact with those excited state neon atoms and stimulate the emission and get this whole process rolling. So in order to produce a whole lot of those excited neon atoms, what happens is we add in a little bit of helium. And it turns out that in helium, there are some excited states of helium that are just by accident at the same energy as this excited state of neon. And the helium actually transfers its energy to the neon into this state and maintains then that very high population of neon atoms here in this excited state. So that's the function of the helium. It's just the energy transfer from the helium excited state to the neon excited state. It keeps the population of the neon atoms really high. So the helium, you don't see that emission, right? That's just a helper in this device, and it's the neon transition that you're looking at here. Okay? Okay, so that was just a short story about the usefulness of knowing about the energy levels in atoms and how ultimately you can make a practical device because you know something about the energy levels of your atoms. Okay. Well, so that's going to finish up right now our discussion of atoms. And now it's time to move on to what chemistry is one of the very important parts of chemistry, and that is chemical bonds and the combination of atoms to form a chemical bond. So that's what we're going to start talking about now. And today what we're going to do is we're just going to talk about the fundamental interactions that are present in every chemical bond. All right? So let's start with that. So let me come over here, and while the lights are warming up so you can see the board. All right, so suppose we have a hydrogen atom here, nucleus A plus charge, and it of course has electron A, it's attached to it, and way out here we have nucleus B and we have electron B, it's attached to it, and they're very far apart. All right, and so in this case where they're very far apart, the energy of interaction is just the energy of interaction between the electron and the nucleus, the electron-nuclear attraction. Here it is, the electron-nuclear attraction. However, as we bring these two hydrogen atoms together, well then at some point, this electron that was only attracted to nucleus A, this electron now begins to experience an attraction with nucleus B. And this electron that was attracted only to nucleus B experiences an interaction whereby it is now attracted to nucleus A. And that kind of mutual attractive interaction then brings those two nuclei closer together. However, at the same time, when you bring those two nuclei closer together, you're bringing the electrons closer together. And so there's an electron-electron repulsion that's present. In addition, as you bring these two nuclei together, well, what's happening here is that you're having a nuclear-nuclear repulsion. Right? So a chemical bond is really the sum of these three interactions and the interplay between these three interactions. And that's what we want to try to look at and try to understand. All right? So how are we going to do that? Well, first thing I'm going to do is I'm going to draw a energy of interaction as a function of the distance between the two hydrogen atoms. All right? So I'm going to take two hydrogen atoms, and I'm going to call the distance between them, I'm going to call that distance between them R. So now I've changed my definition of R. R is the distance between the two nuclei. It's no longer the distance between the nucleus and the electron. All right, I've just changed my definition of R. And I'm going to plot the energy of interaction as a function of that distance between the two nuclei. All right, so here's my energy of interaction. All right. There's going to be a 0 of energy here. And I'm going to plot this as a function of R. And the plot is going to look like this. Way out here, where R is large, I have two separated hydrogen atoms. The energy here is minus 2,624 kilojoules per mole. That's what this energy of interaction is here. Now, as I bring these two hydrogen atoms together, what happens is that this energy is going to decrease. And it's going to keep decreasing until we get to some point. And then as R gets even smaller, that energy of interaction is going to skyrocket and go to infinity. All right? So starting about here somewhere, right, where the energy of interaction is more negative than the separated hydrogen atoms, well, what that means is that we're forming a chemical bond. The two hydrogen atoms are more stable than when they are separated. All right, so the two hydrogen atoms are bound as soon as this energy of interaction gets more negative than the separated atom limit. And it keeps getting more negative. And of course, the value of R at which that energy of interaction is a maximum negative number, well, that's the equilibrium bond length, right? This is the most stable value, the value of R at which the energy is the lowest. It is the most stable configuration. In the case of hydrogen, that value of R is 0.74 angstroms. All right? So, in this potential energy curve, as it's called often, all right, everywhere where this energy of interaction is lower than the separated hydrogen atom limit, everywhere here, this is called the attractive region of the interaction potential. It's attractive because the hydrogen atoms bound are more stable than they are separated, or the hydrogen atoms are bound. They're more stable than the two hydrogen atoms separated. We call this the attractive region of the potential energy curve. We also call this region, this attractive region, we call that the well. Right? It's the well. And the well depth here from the bottom to the separated hydrogen atom limit, if you measure the energy from the bottom up, well, that energy is the bond dissociation energy. I'm going to call it delta E sub D from the bottom here to the separated hydrogen atom limit. That's the bond energy. That's the energy, 432 kilojoules per mole. That's the energy that you have to put into the H2 molecule to separate it. All right, you have to get it from the bottom of this well to the separated hydrogen atom limit here. Now, you can also see here that as you push those two hydrogen atoms even closer together than the equilibrium bond length, you can see that the energy is going back up. And at some point, you push the two hydrogen atoms close enough together such that the energy is equal to that of the separated hydrogen atoms and then becomes greater than that of the separated hydrogen atom. From this value of R on, the hydrogen atoms are no longer bound because their energy is greater than the separated hydrogen atom limit. We call this part of the potential energy of interaction, we call this the repulsive part of the potential. So in other words, as you push the two hydrogen atoms closer together, they form a bond, but if you push them too close, hey, they're going to fly apart. They're no longer bound. All right? This is the general potential energy of interaction for every chemical bond. Every single bond has this general shape. All right? That's important. But that shape is really a consequence of these three interactions that I talked about when we started this problem here. And so what I want to try to do is I want to now try to dissect that curve into the three components that give rise to that curve, that potential energy of interaction, that dependence as a function of R. I want to pull that apart. Okay. So this energy of interaction, what it is the sum of the nuclear repulsion. All right, pushing the two nuclei too close together, there's a repulsive interaction. So that's one of the interactions. Plus the electron nuclear attraction. All right, the electron nuclear attraction is the attraction between the electron and the nucleus on which it came in, and also between the electron and the other nucleus. That's the electron nuclear attraction. Plus the electron repulsion. Well, when you bring this two hydrogen atoms together, those electrons are going to repel. So that's the energy of interaction. It's the sum of those three fundamental interactions. All right, but what I want to do is I want to figure out an R dependence for each one of these interactions. And then the sum of that R dependence should give me a shape that looks like this. So I want to see which interactions are important at what values of R. All right. So let me start. Let's start with the nuclear repulsion here. If I wanted an R dependence for what that nuclear repulsion looked like, what would that be? Coulomb force, right? It's a repulsive Coulomb interaction. Right? It's E squared over 4 pi epsilon naught R. Right? This is just two like charges that are repelling. And so now let me draw that repulsive interaction as a function of R on an energy level diagram. So here's my energy of interaction. It's a function of R. There's going to be a 0 here. Right? And this repulsive interaction is going to be positive everywhere. It's going to be infinite here, and then 1 over R dependence coming down. All right, so this is the Coulomb interaction. This is the nuclear repulsion. That's what it looks like as a function of R. That's one component. Now, what about the other components here? Well, it turns out that I have no simple way of estimating what the R dependence is for the electron nuclear attraction. I have no simple way of estimating what the R dependence is for the electron repulsion. And I have no simple way of doing that for the sum of those two terms. And actually, the sum of these two terms, I'm going to call the electron interactions. right? The sum of these terms, or each one of these terms, involves the electrons. This is electron-electron repulsion, electron-nuclear attraction. This term doesn't have any electrons in it. Okay? So I have no simple way of telling you or estimating what the R dependence is of the sum of these two terms. However, what I can do is that I can figure out what the energy is for the sum of those two interactions at two extremes. I can tell you what the energy is at R equal infinity, and then I can tell you what it is at R equals 0. And therefore, on this plot, I'm going to come in with a value for R equal infinity and a value for R equals 0. I'm going to draw a straight line as an estimate for the R dependence, and then I'm going to add them up and see if the result looks, in fact, like this energy of interaction that I drew for you. All right? And so that's what I'm going to have to do on Friday. So I see you on Wednesday, if not sooner.